So we're going to look at 5.1 and 5.2, and we're going to start out by looking at some common terms that we already know about, but we're going to take these common terms and eventually put them into triangles. So the first thing I want you to do is notice that we have two pictures here, and they're asking what the difference is between a bisector and a perpendicular bisector. And so I grabbed these pictures out of the book for you guys to look at. And if they ask you what the difference is, so this one right here is just a bisector. I mean, he's cool and all, but he's just a bisector, okay? This guy right here is a perpendicular bisector. Now notice you're doing it to segments, and that's because you could never bisect a line or a ray. You have to bisect a segment. So if you bisect a segment, notice that you get P. P is the midpoint of the segment. That's what a segment bisector does. It makes a midpoint. But what's different about a perpendicular bisector is a perpendicular bisector not only gives you a midpoint, but it's also going to make a right angle because it has an extra perpendicular in it. So when you're writing this in, you don't need to watch me write this in, but you want to write it in. You want to say that the difference between a bisector and a perpendicular bisector is that a bisector simply makes a midpoint. That's it. But a perpendicular bisector makes a midpoint and a right angle. And while you're writing that in, I want you to think of how many bisectors you could have on a segment. So as I'm going to look at the first segment, I could draw in a bunch of these, right? So I could start sketching in bisectors. And so when you watch this, when you look up from writing down, you're going to see that I'm drawing a bazillion bisectors of a segment. And that's because there are a bazillion, and maybe a bazillion and one. But if I go to look at a perpendicular bisector, you might notice something. There's only one. So one thing you want to make a note of is when you have a bisector, there are infinite bisectors of a segment. And if you have a perpendicular bisector, there's only one. So he's unique. He's more special than a bisector. So it's not hard to be a bisector, but to be a perpendicular bisector, it takes a little more. Okay, so then it wants you to take your ruler, and it wants you to measure all these segments. So what I'm going to do is I'm going to draw these in, and if you have your ruler with you, you can measure these out, but we're going to just draw in QA and QB, and we're going to measure those. So I've measured them for you. If you want to measure them, you can. So QA is 1.25 centimeters, and QB is 2 centimeters. And so we want to look at what we notice between those. And what we notice is they just simply don't match, right? But then when we come over here and we draw in SJ and SK, and I measure those, I got 2.1 centimeters and 2.1 centimeters. That's jackpot. That means that those distances are the same. And so that only happens on a perpendicular bisector. So it says, what do you notice and which two segments are congruent? So the segments that were congruent were segment SJ was congruent to segment SK. And that is going to be because of the perpendicular bisector theorem. So this is the first time you've seen this theorem. It says if a point is on the perpendicular bisector of the segment, which it was over here, then it is, and this is a new word for you, equidistant. EQUI, distant. It's like equiangular, equilateral, only it's equidistant. It means equal distance from the endpoints of the segment. So as long as I'm on the perpendicular bisector, I'm the same distance from the endpoints. If I'm just on an average old bisector, that does not happen, and you can tell that by the way that I measured these. All right? Then it says, do you think the converse is also true? Well, usually, like the stuff we study in geometry, it is. The converse can be used also, so we're just going to reword the converse by flipping it around. If a point is equidistant from the endpoints of a segment, then it will be on the perpendicular bisector. So the converse also works. Okay, so we're going to take that same idea and we're going to do the same thing but with angle bisectors. So it says, look at the picture below. What does an angle bisector do? So you guys should know now that an angle bisector cuts an angle in half. It basically splits your angle into two congruent angles. You can say that a different way if you want to. Now it says, using your ruler, we're going to draw in two perpendicular segments from D to both sides of ABC. All right, so you can just sketch if you want, but I'm going to lay my ruler on the ray, and I want you to make sure that your perpendicular is making a 90-degree angle, so it should be dropping straight down from D to the ray. And then I'm going to line up my ruler on the other one, and I'm going to drop straight down and make a perpendicular to the other ray. So I'm looking at my distance. Remember, distance is the perpendicular distance. That's my distance to each ray. All right, now it says measure both of those segments. So again, you could take your ruler. I've pre-measured them for you, so I'll put those in the picture. This is 1.2 centimeters, and this is 1.2 centimeters. And so what you're noticing is kind of the same thing that we noticed in a perpendicular bisector. On an angle bisector, these distances match each other. So it says, what do you notice? They are congruent. So this is actually an angle bisector theorem, like the perpendicular bisector theorem. It says if a point is on the bisector of an angle, then it is equidistant from the sides of the angle. Remember, an angle doesn't have endpoints, so you can't say endpoints there. You have to say the sides. And by the way, in parentheses in the back, we want to say that it's always the perpendicular distance, because I told you from now on in the book, when you say distance, it means perpendicular distance. Do you think the converse is true? Well, yeah, like most of these things, it is. You can flip it around. Remember, the original is P arrow Q, and just to review, the converse is Q arrow P. We're just going to flip it backwards. If a point is in the interior of angle, if a point in the interior angle is equidistant from the sides of the angle, then you know for sure that it will be on the bisector of the angle. And these are pretty easy theorems to use. You'll see the problems that you'll have with these, and there won't be much to doing those. Okay, so that's section 5.1. So then we're going to do another video on section 5.2.